We are going to start now the next lecture, lecture 4 of chapter 1, class 11th mathematics, sets. So in this lecture we will talk about some proofs related to the sets and their operations. So we are saying for any two sets A and B, we have to prove this first result, that if A is a subset of B, then complement of B is a subset of complement of A. So what is given to us in this? Given is that A is a subset of B. So what we have to prove is that B complement is a subset of A complement. So we are considering an element in B complement. We consider that X belongs to B complement. So if X belongs to B complement, it means X does not belong to B. Now what is given to us is that A is a subset of B. It means that every element of A is an element of B. So if X is not in A, so this thing implies us that X is not an element of A. This thing means that X is not an element of A. And this thing implies us that X is not an element of A complement. So what we get is that X belongs to B dash. This thing implies that X belongs to A dash. And what this thing means? That B dash, that is complement of B, is a subset of complement of A. So this is our first proof. Second, we have to prove that A minus B, that is equal to A intersection B complement. So we are going to prove this in two parts. We have to prove this equality over here. So we are proving that this first set is a subset of second and second set is a subset of first. So for the first part, for this part, to prove this part, we are considering, let X belongs to A minus B. So this thing gives us that X belongs to A and X does not belong to B. This is by the definition of difference of two sets. So this thing means that X belongs to A intersection B complement, and this is the first part we have to prove. This thing implies us that A minus B, this is a subset of A intersection B complement. Second thing we have to prove is that A minus B is a subset of A intersection B complement. So we consider that an element Y is there which belongs to A intersection B complement. So this thing implies us that Y belongs to A and Y belongs to B complement. This means Y belongs to A and Y does not belong to B. And this is the definition for, this thing is the definition for Y belongs to A minus B. So this whole thing, this what this thing implies us. This thing implies us that A intersection B complement is a subset of A minus B, and this is what we have to prove in our second part. So we are saying we have obtained that this first set is a subset of second and second set is a subset of first. So it is written in the form of superset over here. So basically we have proved these two sets, these are equal to each other. Now the next proof we have is that A minus B intersection B, that is equal to 5. So suppose we are saying that this is not equal to, that is A minus B intersection B, this is not equal to 5. This is, we are supposing this thing, that if possible this is not equal to 5. If this is not equal to 5, it means there is some X, there exists some X such that X belongs to A minus B intersection B. This thing means that X belongs to A minus B and X belongs to B. This thing means, what is X belongs to A minus B means? It means X belongs to A and X does not belong to B and X belongs to B. Now by the associative property, we know that it is AND over here, it is AND over here, so we can write it is X belongs to A and X does not belong to B and X belongs to B. If we put the bracket over here, now what this thing means, that X belongs to B and X does not belong to B, and these two conditions, it is AND over here, these two conditions cannot never hold simultaneously. So we get a contradiction over here, we obtain a contradiction over here. It means that whatever we have supposed that this intersection is not equal to 5, or we have supposed that there exists an X in this set, this thing is wrong. So our supposition is wrong. It means this intersection, this should be equal to 5. Now next we have to prove that A minus B union B minus A, that is equal to A union B minus A intersection B. So to prove this result, again we are proving the two results. One is this is a subset of this set, and then we are proving that this is the superset of this set. By combining these two results, we will get the equality over here. So in the first part, we are going to prove that this first set is a subset of this second set. So we consider that X belongs to A minus B union B minus A. So we are saying it is union over here. So in place of this union, we can write it as OR. So what we get is that X belongs to A minus B or X belongs to B minus A. Now what is the definition of X belongs to A minus B? The definition of X belongs to A minus B is that X belongs to A and X does not belong to B. And the definition for X belongs to B minus A is X belongs to B and X does not belong to A. Now if we look at these two sets over here, we are talking about the Venn diagrams. This is the set A and B we are talking about. We have a universal set U over here. So we are saying that X belongs to A and X does not belong to B. It means we are talking about this region over here. We are saying X may lie somewhere in this portion of A. Second, we are talking about it is X belongs to B and X does not belong to A. Means we are talking about this region over here. So it means X can lie in this region also. So this thing we can also write in the form that we are talking about this. After this, what we are going to write is X belongs to A. Either X belongs to A or X belongs to B. What this thing means, that X lies in this whole region, and we are saying we have next thing we have it is, and the second condition we have it is X does not belong to A. X does not belong to A means when the X is lying over here at B, we are saying the X does not belong to A. X does not belong to this region. Or when X belongs to A, we are talking about when X is lying over here, we are again saying that the X does not lie in the region B. So we are saying or X does not belong to B. So we can write this in the form, this first bracket we are talking about, we can write it as X belongs to A union B and X does not belong to A intersection B. Why we are writing it in this form? We know that when we are saying that X does not belong to A intersection B, it means X belongs to A intersection B complement. And what is A intersection B complement? It is A complement union B complement. What this thing means? That X belongs to A complement or X belongs to B complement. It means X does not belong to A and X does not belong to B. This thing holds over here. So we are saying that this condition that X does not belong to A or X does not belong to B, this is equivalent to the condition that X does not belong to A intersection B. Now from these two results, that X belongs to A minus B and X does not belong to A intersection B, we can write X belongs to the set A union B minus A intersection B. That is, X is from this set, but it does not contain the elements of A intersection B. So what we have proved is, we have started this proof from the result that X belongs to A minus B union B minus A, and we have proved that X belongs to A union B minus A intersection B. So what we have proved? We have proved that A minus B union B minus A, this is a subset of A union B minus A intersection B. So we have proved the first part over here. For the second part, we are saying we have assumed that there is some Y which belongs to this right hand side over here. Then again we are writing this term as, it is minus sign over here, so we are writing it is and it is complement of the second term. Now it is A union B, so we are writing OR over here, it is AND over here, and it does not belong to this, means Y belongs to A or Y does not belong to B. Again this thing will mean we are saying Y belongs to A intersection B complement. It means this is equal to A complement union B complement. And what is A complement union B complement? Because of this union sign, we are saying because of this union sign we have OR over here. So we are saying Y belongs to A complement. It means Y does not belong to A. Y does not belong to B. And from this result, from this step, we will obtain that Y belongs to A and Y does not belong to B, or Y belongs to B and Y does not belong to A. This explanation is given over here. So we can write this result as Y belongs to A and Y does not belong to B, means Y belongs to A minus B, or Y belongs to B minus A. And we can write this is OR over here, so we can write it as union. So the result we get from this, it is that the set A union B minus A intersection B, it is a subset of the set A minus B union B minus A. And this is the second part we have to prove. And by combining both these results, we are saying it is subset over here, this is superset over here, so we get the final answer as equality over here. Now the next thing we have to prove is that A minus B equal to A, this is implied and implied by, this is the symbol for if and only if a my intersection b is equal to phi. So this thing means that we have to, first we have to prove that a minus b is equal to a implies a intersection b is equal to phi. Second we have to prove is that a intersection b is equal to phi. This implies that a minus b is equal to a. We have to prove these two things. So for the first part we are saying we consider this thing is true, that is given is this, and we have to prove that this is equal to phi. So we are saying if possible let a intersection b is not equal to phi. It means there is some x which belongs to a intersection b. So this thing implies us that x belongs to a and x belongs to b. We are saying x belongs to a intersection b. This thing implies us that x belongs to a and x belongs to b. Now what is given to us is that a is equal to a minus b. So this thing means that x belongs to a minus b and x belongs to b. Now if x belongs to a minus b, this means x belongs to a and x does not belong to b. And this second part we have and x belongs to b. So this thing we can write it in the form that x belongs to a and we have bracket over here, it is x belongs to does not belong to b and x belongs to b. We are talking about this condition over here that x does not belong to b and x belongs to b, and we are saying that both these conditions, that x belongs to b and x does not belong to b, both these conditions can never hold simultaneously. We are talking about these conditions over here, that these two conditions they cannot never hold simultaneously. It means this supposition that we have made that a minus b is not equal to phi, this is a not true, this is not possible. So we obtain a contradiction over here. It means this supposition is wrong and hence a intersection b should be equal to phi. Next we have to prove is the second part, or this thing we have to prove. Now it is given to us that a intersection b is equal to phi, that is a and b they are disjoint sets. We have to prove that this implies that a minus b is equal to a. So when we have to prove that a minus b is equal to a, it means we have to prove two things. We have to prove that a minus b is a subset of a, and we have to prove that a is a subset of a minus b. To prove this first part, we are saying let x belongs to a minus b. So this thing implies us that x belongs to a and x belongs to b. Complement. From this it is clear that x belongs to a. We are saying this thing implies us that x belongs to a. This is at least. This is the another condition that x also belongs to b. Complement. So we are saying this is the least condition we have, it is that x belongs to a. This is at least, and this thing means that what we get from this is we are saying that x belongs to a minus b. This thing implies us that x belongs to a. Both these conditions they implies us that a minus b is a subset of a. For the second part, we are saying let x y, there is an element y which belongs to a. This thing implies us that y does not belong to b. Why? Because this condition we are already supposing over here that a intersection b is equal to phi. So if y belongs to a and b they do not have any common element, it means that y cannot belong to b. So what we get is that y belongs to a and y does not belong to b, and this is the definition for a minus b. So what we get is that for each y belonging to A, we have y belongs to A minus B. For each y belongs to A, y does not belong to B. So we get these two by combining these two results. We're talking about A minus B is a subset of A and A is a subset of A minus B. By combining these two results, we obtain the final result that A minus B is equal to A, and this is what we have to prove. So we are saying we have proved both the conditions, both the implies sign we are talking over here, that if this thing is true then this thing holds, and if the second part is true then this first thing holds, and this is what this implies and implied by sign means over here. Next we have is if A union B is equal to A intersection B, we have to prove that A is equal to B. So this thing is given to us. We are saying given is that A union B is equal to A intersection B. We have to prove that A is equal to B. So we are saying we have to prove A is equal to B means we have to prove two things, that A is a subset of B and we have to prove that B is a subset of A. Now for the first part we are considering that let there be an arbitrary element x from A. Now what is given to us is that x belongs to A. So this will implies us that x belongs to A union B, because x is an element of A. So x will be an element of A union B, and it is given that A union B is equal to A intersection B. So this thing means that x belongs to A and x belongs to B. So this thing means that x belongs to B. It is and over here. It means x belongs to both A and B. It means x belongs to B. This thing is sure. So what we get is that x belongs to A implies x belongs to B, and this thing means that A is a subset of B. Second, we are talking about suppose there is an element y that belongs to B. So y belongs to A union B. It means we have y belongs to A intersection B. It means y belongs to A and y belongs to B, and this thing means that y belongs to A. This is surely we have that y belongs to A. So from this result we are getting that y belongs to B implies y belongs to A, and this thing implies us that B is a subset of A. Now combining both these results, that is A is a subset of B and B is a subset of A. Now by combining both these results, we will obtain that A is equal to B. Now the next we have to prove is if A is a subset of B, then for any set C, we have to prove that C minus B is a subset of C minus A. So given what is given to us is that A is a subset of B. This thing is given to us, and we have to prove this thing. So we are considering the left hand side over here, and we are saying let x be any arbitrary element of C minus B. Then what this thing means, that x belongs to C and x does not belong to B. Now it is being given that A is a subset of B. So we are given over here that x does not belong to B. So and A is a subset of B. So this thing implies us that x does not belong to A. We are saying x is not an element of B. From this it is clear that every element of A is an element of B. So what we can write from this is that x belongs to C and x does not belong to A. So this gives us that x belongs to C minus A. and this is what we have to prove. We are saying that x belongs to C minus B. This thing implies x belongs to C minus A. So what we get is that C minus B is a subset of C minus A. This is what we have to prove. Now next we have to prove that for any two sets A and B, A union A intersection B, that is equal to A. Now if we look at this element A intersection B, it is clear that it will be a subset of A, because A intersection B, it contains the elements A which are in A and in B. It means it is contained in the set A. And we know that if X is a subset of Y, then this implies us that X union Y, that is equal to Y. This result we have already proved. So if we substitute what result we have, this is just like this, X is equal to A intersection B and Y is just like B. So if we substitute these values over here, we get A intersection B union A, that will be equal to A, and this is what we have to prove in our first part. Second we have is A intersection A union B is equal to A. Now in this result, what we can see is that this A is always a subset of A union B. Again, we are substituting the values in this formula that X is a subset of Y. This thing implies us that X intersection Y is equal to X. In place of X we are writing it is A. In place of Y we are writing A union B. So the answer we obtain is that A intersection A union B, that is equal to, this is X over here, and this is equal to A. Next we have is for any sets A and B, we have to prove that A intersection B union A minus B is equal to A. So we are writing the left hand side, it is A intersection B union A minus B, we know the value, it is A intersection B complement. So what we get is this is equal to A intersection B union B complement. This result we are obtaining by using the distributive property, and we know that B union B complement, that is equal to the universal set, and A intersection the universal set, that will be equal to A, and this is what we have to prove. Now the second part we have, the LHS we have for the second part, it is A union B minus A. So that is equal to A union B. B minus A means we are talking about B intersection A complement. When we apply the distributive property, we get it is A union B intersection A union A complement. So it is A union B intersection. What is A union A complement? That is equal to the universal set, and intersection with the universal set, it is the set itself. So the answer we obtain, that is A union B, and that is equal to the right hand side. Now the next question we have is, if A intersection B complement is equal to 5, then prove that A is equal to A intersection B, and hence show that A is a subset of B. So we are saying what is given to us is that A intersection B complement, that is equal to 5. Now we have to prove that A is equal to A intersection B. So we are writing A is equal to A intersection the universal set. We can write this universal set as this is equal to A intersection B union B complement. So this thing gives us this is equal to A intersection B union A intersection B complement. It is given that A intersection B complement this is equal to phi. So what we are left with is A intersection B union phi, and the answer we obtain that is equal to A intersection B. This is what we have to prove. Now next thing we have to prove is that A is a subset of B. Now it is what we have is A is equal to A intersection B. We have to prove A is a subset of B. So let us suppose that an X belongs to A and A is equal to A intersection B. So this thing implies us that X belongs to A intersection B. This thing implies us X belongs to A and X belongs to B. And this thing implies us X belongs to B. This is surely we have X belongs to B. So what we have is that X belongs to A. This implies us that X belongs to B. What this thing means? That A is a subset of B. This is what we have to prove in our second part, that A is a subset of B. Now the next result that we have to prove is that if A, B, C be the sets such that these are the conditions given to us, that A union B is equal to A union C, A union B is equal to A union C, we have to prove that B is equal to C. So we start with this condition that A union B that is equal to A union C. Now if we take the union intersection of B on both sides, now what this term will become? We are saying B will be a subset of A union B. So this term will be equal to B, and this is equal to A intersection B union C intersection B. And this value we are saying, this B value we obtain, it is equal to this. Now in this next step, we are again starting with this equation, this first equation we are talking about. It is A union B that is equal to A union C. Now we are taking the intersection with the set C. Now on this side we can see that C is a subset of A union C. So this term will become C, and this is equal to A union B intersection C. So what we get is that C is equal to A intersection C union B intersection C. Now over here it is given that A intersection B that is equal to A intersection C. So in place of A intersection C we can write, in place of this term we can write this is A intersection B. Now look at these two terms, it is A intersection B union C intersection B. This term is A intersection B union B intersection C. So we are talking about the right hand side of both these equations, they are equal. So it means what we get is that B is equal to C, and this is what we have to prove. Now the next question we have, for any sets A, B and C, we have to prove the following results. The first thing we have to prove is that A minus B union C that is equal to A minus B intersection A minus C. So we start the proof with the left hand side, and it is given to us, this is LHS, we are saying it is A minus B union C, and we know the formula for A minus B, it is set A. This complete set we are talking about, this is just like B, and we are saying this is A minus B. So it is A intersection B union C complement. We are saying A minus B means those elements of A which are not present in B union C. So by using the De Morgan's law on this, we obtain this is equal to A intersection B complement intersection C complement. This is equal to A intersection B complement intersection A intersection C complement. What is the A intersection B complement? This is those elements of A which are not in B. So this is equal to A minus B intersection A minus C, and this is what we have to prove. This is equal to the right hand side. Similarly, the next we have is A minus B intersection C. Earlier it was B union C, now it is B intersection C. So we obtain it is A minus B intersection C. This is equal to A intersection B intersection C complement. Again, on this term, we are using the De Morgan's law, and we obtain this is equal to B complement union C complement. Now separating these two terms, we obtain this is equal to A minus B, and this term is equal to A minus C, and this is what we have to prove. Now coming to the third part, we have in this part we are saying the LHS we have, it is A union B minus C. So we can write this is equal to A union B intersection C complement. This is equal to A intersection C complement union B intersection C complement. This is equal to A minus C union B minus C. Similarly, for this last part, we are saying we have to prove that A intersection B minus C, this is equal to A minus C intersection B minus C. So same thing we are doing over here. This time we have written it is A intersection B intersection C complement. We have separated these two terms and we obtain this answer. So in these four results, we have used the De Morgan's law that says A intersection B complement, that is equal to A complement union B complement, and A union B complement, that is equal to A complement intersection B complement. So these are the results that we are using to prove these results. Now next we have given, let A and B be two sets, and this condition is given to us that A and X and B and X, both these sets, these are disjoint sets. Second condition that is given to us is that A union X is equal to B union X for any set X. Then we have to show that A is equal to B. Previously we have proved that if we are given A union X is equal to B union X, then we have shown that it is not necessary that A is equal to B. This thing is not necessary. But over here we are saying this condition, with this condition, another condition is given to us that this A and X and B and Y, both these are disjoint. Then we are saying A is equal to B. I am again repeating this thing, that if only this condition is given to you, without this condition, then it is not necessary that A is equal to B. So we start this proof. So we are writing what is given to us is that A union X is equal to B union X. Now we take intersection with the set A on both the sides. Now by distributive property we are saying it is A intersection A union A intersection X, that is equal to A intersection B union A intersection X. Now what is this value? A intersection A, this will be equal to A intersection X, this is given to be 5. This value is given to be 5. Then this is equal to A intersection B union A intersection X. Again, A intersection X is given to be 5. So what we are left with is that A is equal to A intersection B. And if A is equal to A intersection B, then this thing means that A is a subset of B. Why we are proving this? Because we have to prove that A is equal to B. It means we have to prove two things, that A is a subset of B and B is a subset of A. So first part we have proved, that is A is a subset of B. Now second thing we have to prove is that B is a subset of A. So to prove this, again we are starting with the same thing. It is A union X is equal to B union X. Now we take the intersection with this term we are saying over here, we are taking the intersection with the set B. We get it is B intersection A union B intersection X, that is equal to B intersection B union B intersection X. Now B intersection X it is 5, B intersection X it is 5, B intersection X B it is B. So what we are left with is that B intersection A, that is equal to A, and this thing implies us that B is a subset of A. So we have proved two things. One is A is a subset of B and B is a subset of A, and by combining both these results, we are saying A is a subset of B and B is a subset of A. By combining both these results, we obtain the answer that A is equal to B. Next we have to show that the following four conditions are equivalent. Following four are equivalent means that one is implied and implies two. What we have to prove is that one implies and implied by two. This is implied and implied by, implies and implied by 3. This implies and implied by 4. We have to prove this thing. So in place of proving this, what we are going to prove is that 1 implies 2, implies 3, implies 4, and 4 implies again 1. So if we could prove this thing, it means that all these conditions, these are equivalent to each other. So first we are saying, we are considering, let, the first thing we are going to do is we are saying let A is a subset of B, and we have to prove that it is proper subset over here. A is a subset of B. This is given to us. We are assuming that this is given to us, and we have to prove that A minus B is equal to 5. So when we are talking about this condition, we are saying what is A minus B. A minus B means we are saying this is this set is X such that X belongs to A and X does not belong to B. But what is given to us is that A is a subset of B. When A is a subset of B, this thing is given to us. So what is given to us is that for all X belonging to A, X belongs to B. It means this collection, we want to find some X which belongs to A but does not belong to B. We cannot find any X in this form. So it means this collection is equal to 5. So this is our first proof. We are saying that A is a subset of B implies A minus B is equal to 5. That is, it is an empty set. Second thing we have to prove is that given to us is that A minus B is equal to 5, and we have to prove that A union B is equal to B. So to prove this, we are saying that when A minus B, that is equal to 5, that is an empty set. So what this thing means, that every element of A is an element of B, that we cannot find any element of A which is not the part of B, that is not the element of B. So this thing implies us that A is a subset of B, and we know that if A is a subset of B, then A union B is equal to B. So we have proved that if A minus B is equal to 5, so this thing implies us that A union B is equal to B. So we have proved that 1 implies 2. Next we have proved 2 implies 3. Next we have to prove that this 3 implies 4. So 3 implies 4 means we have started with this condition that it is given to us that A union B is equal to B. Now we are saying when A union B is equal to B, this thing implies that A is a subset of B, and if A is a subset of B, then we have A intersection B is equal to A. So this proves that 3 implies 4, and similarly when we are proving this last part, that is 4 implies 1, we are saying what is given to us is that A intersection B is equal to A. So A intersection B is equal to A means that if we consider X belongs to A, then this implies X belongs to A intersection B, and this means X belongs to A and X belongs to B, and this implies X belongs to B. This is surely, this is true. So what we get is that for X belongs to A, we have X belongs to B, and this condition is equivalent to the condition, but this is the definition of A is a subset of B. This is the definition of A is a subset of B. So we have proved that this 4 implies 1. So we are saying we have proved all these conditions, that 1 implies 2, 2 implies 3, 3 implies 4, and 4 implies 1. It means all these 4 conditions, these are equivalent to each other. Next is for any sets A and B, we have to prove that power set of A intersection B, that is equal to power set of A intersection power set of B. It is being mentioned over here that X as element of power set is a set. Why we are saying this thing? We are saying when we are writing a set X, say it is equal to 1, 2, and we are writing the power set of X, then the power set of X, it has elements 5, 1, 2 and 1, 2. It is important to note over here that these elements themselves, they are sets. This thing is mentioned over here, that the elements of the power set, they themselves are the sets. So if we have to prove that these two sets, they are equal to each other, it means we have to prove that power set of A intersection B is a subset of power set of A intersection power set of B. Second thing we have to prove is power set of A intersection power set of B, that is a subset of power set of A intersection B. So to prove these results, we are saying for the first part, we are considering, suppose it is given that we are proving this first part over here. So we have assumed that there is some X which belongs to power set of A intersection B. So it means we are talking about in place of the small x, we will write it as capital X over here, because we have seen over here that this X is itself a set. So that is why we are using this capital X in place of small x when we are considering the element of a power set. Now again, if you look at this example over here, we are talking about this example over here. So what we can see from this example is, suppose I am saying this set 1, this belongs to power set of X. First thing, this is a set, the element of the power set, it is a set. Then what we have is that this set 1, this is a subset of the set X. This is the subset of the set X. So same thing we are using over here. We are saying if an element, this is a set X, it belongs to the power set, then what we have is that this set X is a subset of A intersection B, that is it is a subset of the given set. So what we get is that X is a subset of A and X is a subset of B. Now if X is a subset of A, it means X belongs to power set of A and X belongs to power set of B, and this thing is equivalent to X belongs to power set of A intersection power set of B. So this proves our first part, that power set of A intersection B is a subset of power set of A intersection power set of B. To prove the second part, we are considering this term over here, and we are saying suppose Y belongs to power set now of Y belongs to power set of A intersection power set of B. Again, this Y is itself a set because it is element of power set. So we are saying this Y is a subset of, we can write, or before writing this term we are writing that Y belongs to power set of A and Y belongs to power set of B. So this thing gives us that Y is a subset of A and capital Y, it is a subset of B. So this gives us Y is a subset of A intersection B, and this is what we have to prove. So we are saying that if Y belongs to power set of A intersection power set of B, this thing implies Y is a subset of A intersection B. So what we get is that power set of A intersection B, this is a subset of power set of A intersection B. Now combining both these two results, we obtain that power set of A intersection B, that is equal to power set of A intersection power set of B. Next is, for any two sets A and B, we have to prove that power set of A union power set of B, that is a subset of power set of A union B. And further it is given, we have to verify whether is the converse true or not. So to prove this result, we are considering an element from this set. We are saying suppose X belongs to power set of A union power set of B. So this thing should be clear to you now, that why we are writing capital X, because this capital X is itself a set as it is the element of a power set. So we are saying this implies that capital X belongs to power set of A or capital X belongs to power set of B. This thing implies that X is a subset of A or X is a subset of B, and this implies that X is a subset of A union B. So what we get is that for X belonging to power set of A union B, X is a subset of this, and this thing implies that X belongs to power set of A union B. We are saying if X is a subset of A union B, then X belongs to power set of A union B. So this thing proves the result that we have to prove that power set of A union B, that is a subset of power set of A union B. Now in the previous result, we have seen that power set of A intersection power set of B, it is also a subset of power set of A intersection B. But when we are talking about, in place of intersection, we are talking about the union, we are saying this result does not hold. And when we have to prove that this result does not hold, so if we give one counter example, then that will be sufficient. So the example that we have given over here, we are saying that the set A is equal to 1, set B is equal to 2, then A union B is equal to 1, 2. Power set of A will be 5 and set 1. Power set of B is 5 and set 2. And power set of A union B, it has 4 elements in this form, and we can verify. Now when we are calculating power set of A union power set of B, we obtain the answer in this form. These are the two values, it is power set of A and this is the value of power set of B. On taking the union of both these values, we get this answer, and clearly we can see that both these sets, these are not equal to each other. So it means that the converse of this is not true, that P of A union B is not a subset of P of A union P of B. This result is not always true. Next we have is, if power set of A is equal to power set of B, we have to prove that A is equal to B. So what is given to us is that power set of A is equal to power set of B. Now we have to prove A is equal to B. It means we have to prove two things. One is A is a subset of B, and second is B is a subset of A. We have to prove these two things. Now we are talking how we prove this is, first part I am talking about, we are writing A is a subset of A. This thing is always true. So we are saying A belongs to the power set of A, and it is given that power set of A is equal to power set of B. This thing is given to us. So what we get is that A belongs to power set of B. So this thing implies us that A is a subset of B. Similarly, we are saying B is a subset of B. This thing implies us that B belongs to power set of B. This thing implies us that B belongs to power set of A, because it is given that power set of A and power set of B, these are equal. So this thing implies us that B is a subset of A. So we have two results over here. One is A is a subset of B, and second we have B is a subset of A. Now combining both these results, that is B is a subset of A is a subset of B, by combining both these results you obtain that A is equal to B.